Hi everyone, welcome back to another video in the LLMs related playlist. In this video, we are going to see about a latest model which has been on trend in the internet, which is from the organization known as Mistral AI, known as the model being Mistral 7B. This model has said to be outperforming the 13 billion model of Llama, also 34 billion at many benchmarks. So you can see that it is almost outperforming the models which are of 5x its size. So in this video, we are going to see how to fine tune this model on a custom use case, and also we'll be seeing what is it that powers this model behind. So without wasting time, let's jump into the video right. So here is the blog from Mistral AI themselves. Here they have stated that Mistral 7B is the best 7B model up to date, which is true because the benchmarks shows that it is not just outperforming 7 billion models like Llama or else whatever 7 billion models are there at the market right now, but it is also outperforming Llama 13 billion and 34 billion. So 34.7, it is almost 5x size, which means it is true. They are the best 7B model up to date. And here if you see, they have claimed the same, and they are also saying that it provides almost the same performance of Code Llama 7B, which has provided tremendous performance when it comes to code. And if you haven't checked, guys, I've also shown you how to make fine tuning on Code Llama for your own use case. So if you haven't checked it out, do check it out. So here also they have said that it provides almost the similar performance of Code Llama. And here if you see, they have said that they have used grouped query attention for faster inferencing and sliding window attention for handling longer sequences. So what does these two mean? You see, even in the previous video of DesiLM, where I said that it inferences almost 5x of Llama, they have also used variable group query attention. It was variable group query, okay? But here they have used group query. And the interesting fact here is, I read somewhere that this guys of Mistral AI, this is a French startup if you don't know, and the guys working here are the creators of Llama 1 actually. So Llama 1 was created by these guys. So it is great that they stuck up on the same architecture because it also looks like Llama, the way the model looked like when it comes to the config and the layers present inside. It looked like Llama, and yeah guys, it has given some tremendous performance. You will see, so stay till the end of the video and you will understand why I'm saying that. So here you see the main thing which is outperforming, that is all fine, okay? It is outperforming than any other model, that is all great, okay? Because there are a lot of model which is claimed recently that it is outperforming Llama, it is outperforming GPT-4. For example, one of our recent videos I have said that Xwin outperformed GPT-4. But you see, all of those models has used Llama to 7 billion as their base, if it is a 7 billion model obviously, and all the restrictions of Llama applies similar to this model also. But here these guys have released it under Apache 2.0 license, and it can be used without any restrictions, which means you can also use it for your commercial purposes. That is an amazing thing because this is an open source beast right now, okay? So here if you see, they have said that it is very easy to fine tune on any task, and they have also fine tuned on chat, it seems, which also outperformed its respective variant, like Llama to 13 billion chat. It also outperformed Llama to 13 billion, which is the base. And once they fine tuned Mistral 7B on chat, it outperformed Llama 13B chat also, okay? So here is the performance graph, okay? So it is pretty good. So let me show you. So the orange one is Mistral, and red is Llama to 7 billion, and blue is Llama to 13 billion, and light green is, it's not blue, I think it's teal, yeah, teal. And then light green is Llama 134 billion, okay? So if you see in MMLU, which is massive multitask benchmark, so let me show you here. It is a famous benchmark, everyone. So you can see here, multitask language understanding. It will have multiple number of tasks, and trust me guys, it won't be very easy. And this model has given a tremendous performance. It is around 60 billion. And here if you see, Llama to 7 billion, it's approximately 45. It is almost 15% higher. And when we come to knowledge and then reasoning, it has slightly lesser performance than Llama 134 billion, but in case of Llama to 7 billion and 13 billion, still it has outperformed. So similar case retains with every scenarios. So here if you see in reasoning, it has almost similar performance of 34 billion, but it outperforms 7 and 13. So you can say that it outperforms 7 billion and 13 billion, and it almost gives a state of that performance like 34 billion also. So yeah guys, I'll also provide this link so that you can go in detail. And here if you see, they have given the benchmarks which they have performed, that their in form of table they have given it. So here you can see in MBPP, except that benchmark and human eval, it has outperformed the other models at every aspect. So that is pretty cool actually. So here if you see, it has been close to NQ by 0.2%, which is very negligible. And when you come to trivia QA, still this is higher by negligible percentage. And when it comes to human eval, it is slightly lesser, like by 0.5%. The only place where it has failed, which is against Code Llama, is in MBPP benchmark. Okay, and that is for code. And this one is a general purpose LLM, and it is not created explicitly for code, and it also gave almost similar performance from Code Llama. So that is pretty good. Okay, so here is a graph which shows that it is better than 13 billion, almost similar to 34 billion, but very less than to 70 billion, because there are some people who can afford 70 billion, but if we want to run it on 7 billion models, this is our go-to model right now guys. And here if you see, they have used sliding window attention, okay, which will help you to handle large sequences with lesser cost. Okay, so you will be able to handle large number of sequences where a window of attention will be moving out. So I won't be explaining this in detail, and if you want an in detail video on this as well as group query attention, let me know in the comment section everyone. I'll try to make a video on that. So finally, when it comes to chat, Mistral 7B Instruct has been the second best model, or rather third best model here, coming next to Wizard LM and Vicuna. Other than that, it has outperformed Llama to 7 billion chat, Llama to 13 billion chat and all. So yeah guys, we know that now this model is pretty good. So next, let's see if there is any new thing which we need to know from the Hugging Face them. So we know that sliding window attention is used, where they have used it, they have trained it on 8K context length, and the theoretical attention span, like I said, right, the window length, so that you can move. So almost like, you can handle at least 128K tokens. That is what is claimed due to the sliding window attention. And when it comes to group query attention, it will allow you to do faster inferencing. And this is interesting guys. There is this tokenizer which they have used, known as byte fallback BPE tokenizer. And this tokenizer, what it will do is, it will ensure that no token will be a UNK token. So if you are wondering what is UNK token, for example, if you have vocabulary, right, if there is a token which comes up and that is not there in your vocabulary, it will still handle it. So that is what is bytefall BPE tokenizer. And yeah, so that is what we need to know from the Hugging Face documentation. So in this video, we are going to fine tune this model, which is Mistral 7B Instruct V0.1. Okay, so here if you see, the model is almost 15 gigs, and like in the last video, similarly we are also gonna fine tune still by using GPTQ. Okay, so GPTQ is the only way which we can fine tune right now, because this model is pretty huge. All right, so let us have this for later part. Okay, so here is the fine tuning script everyone, and here if you see, let me show you one thing. Here if you see in the documentation itself, they would have said that you are viewing main version which requires installation from source. If you would like to do regular pip install, do check out version v4.33.3. See the thing is, still it is not yet released in the transformers package. Okay, the pip version is not ready yet. So what they would have said is install from source. Okay, so that is why we would have done the installation slightly different here. So as usual, before going on to fine tuning, let me show you the results, everyone, so that you will also know what is the use case which we are gonna do. So in this video, we are gonna do a custom use case which is to summarize the dialogue. Okay, whatever conversation is there, it will try to summarize it. So here, if you see, I would have said summarize this following dialogue. Vasant is saying that I'm at a railway station in Chennai. Karthik is saying no problem so far, right? Like something like that. It is he is questioning, and Vasant is saying no, everything is going smoothly, and Karthik is again saying good, let's meet there soon. So the assistant, which is our model Mistral, has responded that Vasant is at a railway station in Chennai, everything is going smoothly, he will meet Karthik soon, which is pretty accurate, right? So that good is Mistral 7B, everyone. And if you see, the inference also has not been too long. It took me only 2.89 seconds. Yes, it ran in GPU, so that is there, but still 2.89 is a pretty good inference time. Okay, so now that we know that this model is doing very well, I'll show you what are all the installation needs to be done. Okay, so if you see, I'm installing accelerate, peft, bits and bytes, transformers from the source, and then TRL, AutoGPTQ, Optimum. All are not new. We would have used all of these in some previous videos. Anyways, I'll let you know what are the purposes. Accelerate is for some GPU computation related functions, and PEFT is for LoRa and PEFT adapters. Basically, LoRa is also a PEFT adapter, right? So to use LoRa, will be importing PEFT. Bits and bytes, it is for quantization related things, but in this video you would not need that. For ensuring safety, I just installed that also. And we are installing transformers from source, TRL, so that we can use SFT trainer from transformers reinforcement learning library, and AutoGPTQ, so that we can work with the GPTQ quantized model, and finally Optimum, which is also a requirement when you're fine tuning GPTQ models. Okay, so here if you see, I would have also imported this library called Pi7ZR, which was a requirement for the dataset we loaded here. Okay, so that is about the dependencies. So as usual, you need to log into your notebook, and this is the dataset which we are going to use, known as Samsung. Okay, so but this is not commercially licensed, which means you can't use it for commercial purposes. But yeah, we are not doing for commercial purposes, right? We are just checking how to work with this. So here you see, here is an example. There is a conversation and there is a summarization for that. Okay, so this is the dataset which we are using, and as usual, we'll need everything to be under a single column, which is, or a single field, which is text as usual. So what I would have done is, I would have combined this dialogue and summary in a way, so which I'll show you right now. So we are just loading the train split from the dataset, and we are converting it to pandas data frame for easier processing. And here if you see, I'm calling the dialogue and summary column, and on which I'm applying a lambda function. What it will do is, it will try to combine dialogue and summary in such a way that before dialogue, I'll be having a prefix stating that this is from human, and human is saying summarize this following dialogue, and the assistant will respond with the summary. Okay, so that is how it is created. So I'm also printing the first sample so that we can check if we have processed it correctly or not, and then we are again converting it into Hugging Face dataset so that we can still use it for our training. Okay, because it won't accept a data frame, it will require a Hugging Face dataset. So that is why we are doing it here. Next, if you see, we are calling the tokenizer from Mistral 7B instruct v0.1 GPTQ. So this is the model which we need to see right now. Let me open it here. Sorry. So here it is. This is Mistral 7B instruct v0.1 GPTQ, which is of size 4.16 gigs. All right. So that is the model which we are going to use right now, and it is from TheBloke as usual. And we are also calling the tokenizer from here itself because the tokenizer is available. Okay. So here if you see, we are setting the pad token to be UOS token, and we are setting the GPTQ config with bits is equal to 4, and we are also providing the tokenizer. Alright, so I hope I'm clear till now. The next step would be to call the model. So here if you see, we need to provide the model checkpoint which we have provided here. And along with that, it will also expect a quantization config, which is the GPTQ config, which we called here, and that is also provided, and device map, so that it will try to map the device to layers, which we are saying it as auto. What it will do is it will try to map everything to a single device, because this is single GPU, right? Only one device is there, CUDA 0. It will try to map onto that. So we are just printing the model for one purpose, which I think you would all know. Before showing the code, I would like to ask you all to let me know in the comment section why I have printed the model here. So if you have watched our previous videos, I guess you should know by now. We are setting use catch as false, so that we are setting it to training. Pre-training TP is equal to 1, so that we can replicate the pre-training performance. And we are also setting model gradient checkpointing enable, and this is very important, guys. Prepare model for k-bit training. So what it will do is, here if you see, we are training it in int 4. Okay, so it will ready prepare the model for int 4 training. If you don't call this right, you will be always facing code out of memory error. So what I would say is, please ensure that you have done this. Along with that, you should also call this function known as getPef model. Okay, so here if you see, I would have called it getPef model here. So what it will do is, based on the model you created here and the config you created here, which is having a LoRa rank of 16, alpha as 16, dropout as 0.05, bias as none, task type as causal LM, and if you have predicted correctly, kudos to you everyone, it is target modules. That is why I have printed the model here. So like I said, it is almost similar to Llama, so the keys also didn't change a lot. It is qproc and vproc. Okay, but yeah, I would request you all to try with different modules as usual, and as like we saw in the platypus video, it might give some better performance if you do it for all linear layers. So try it and let me know everyone. So now coming on to the training arguments, I'm providing the output directory, which is usual per device train batch size. What it'll do is it will allocate 8 training samples for each device. So in this case there is only one GPU, but if you had 10 GPUs it will become 80. I hope you all understand. And gradient accumulation steps is 1. Optimizer is page random W 32-bit, because we are working with quantized training. We are doing a quantized training, right? Quantized model training. We are using page random optimizer, and we are setting the learning rate is 2e minus 4. Learning rate scheduler is cosine. Save strategy being epoch, and logging steps being 100, so that we can log at every 100 steps. And the number of training epochs is 1, which won't make any sense because of the max steps being set to 250. So what will happen is, relatively 250 into 8, so 254 is 1000, 258 is 2000. So 2000 samples only will be trained on. So here we have 14,000 samples, but only 2000 samples will be trained, and then the training will be stopped. We are doing a mixed precision training by setting FP16 is equal to true, which will train on float precision 16. And finally, we are setting push to hub is equal to true, so that we can push the adapter model into the hub, so that we can call it at the later half whenever we want to do inferencing and all. Okay, so that is about training arguments. And finally, we have our trainer here, for which we need the model. The model should be this one. Okay, once you call the getPef model, after that only you should provide it here. And data, which is data of text. Okay, so you might think, well, how it will take the text alone, because we are providing data set text field to be text. It will take the text field alone. Okay, and the pef config is provided from here, as we have done previously. We know what it is there. And we are also providing the training arguments, tokenizer, and max sequence length being 512, which will take 512 tokens as its input length. Okay, finally we are calling the trainer.train function, which will train the model, and push to hub function, which will push the adapters alone. Just remember guys, it won't push the base model, it just push the adapters. You should call the real base model, not the real model, base model, and combine it with the adapters again for inferencing. Just remember that. Okay, so this is fine tuning Mistral 7b function, which if you call here, it will train. So here if you see, this is the model, and they have used a different linear function known as quant linear. Okay, they have a separate class called Mistral attention, separate class called quant linear. Okay, so they have used silly activation function, Mistral RMS norm. They have tried to customize a lot actually. Okay, and if you see, the inner dimension which they have worked on is 4096. Okay, so that is about the model. And if you see, the loss which we have ended up is on 1.77 for a dataset which it has in seen prior. It is pretty good because we have just run it on 2000 samples. But if I'm very sure that if we run it on some n number of samples, like even if we complete the training till one epoch also, I'm sure that we'll reach a loss of around 1.00. Okay, which is pretty good. So I'm just saving this adapters in the drive because just for local saving purposes. And before doing that, try to ensure that you have mounted your drive. Okay, by clicking this button here, you can mount the drive. So once you mount the drive, you can just save it. I hope you have all done it. So once you mount the drive and save it, you are done with the model training part and you are ready for inference. So now coming on to inference, we'll be calling autopef model for causal LM. What it will try to do is it will try to take the adapter, and based on that it will call the base model by itself and it will combine it and provide you the model directly. So basically they will do whatever it's needed and we can just call a simple class alone and provide the path. That is enough. Okay, so we are providing the tokenizer, which is Mistral Finetune Samsung, which is the one which we done right now. And I'm providing the tokenizer with the input which we saw already. I'm at the railway station in Chennai. Karthik replying no problem so far, and Vasant saying no, everything is going smoothly. Karthik is saying good, let's meet there soon. So, and we are stopping with assistant. And guys, if you're wondering what is this format of prompt is known as alpaca format. Okay, so I wanted to show you all, but I couldn't show in the last video. So let me show it here. Alpaca prompt template. So here if you see, they would have used this actually, prompt input and response. Okay, so they would have called like this, instruction response. So this is how it will work. Okay, so they would have said a simple thing like, below is an instruction, but we don't have the instruction, so I didn't provide that, but we are just following the same format as alpaca. Okay, so yeah, this is alpaca prompt format. So now we are calling the model, we are providing the path obviously, and we are setting the low CPU memory usage to be true, so that it will consume memory usage of CPU will be very less obviously. And we are setting the torch D type to be float 16 and device map is CUDA, or else even also you can provide a dict with an empty string being key and the value being 0, which will obviously map all the layers to CUDA 0 device. Okay, so that is what is about the model. Now coming on to generation config, why we have provided separately is, like when you call the model.generate function, if you have lot of parameters in it, it will look ugly. So when you call this generation config, it will be looking very easy to understand also. And here I have said do sample is equal to true, which is need to be provided when you provide temperature. Temperature is provided as 0.1. So temperature parameter is used to control the randomness of the generation. When you provide close to 0, it will be very strict, and when you provide close to 1, it will be trying to be very creative. Okay, and top k is equal to 1. What it will do is it will try to provide the top most probable generation. Okay, so this is a separate concept which is known as sampling. So if you also want video on that, how greedy search works, how beam search works, how the sampling works, let me know again in the comment section. I'll try to make a video on that very soon. Okay, so now coming on to temperature, I've already said you how it works, and I've provided max new tokens is equal to 25 because I don't want to generate more than 25 tokens because the summary is pretty less, right? Because they are not providing a lot. By setting it to some smaller values, we can also do the inferencing pretty faster. And we are setting the pad token ID to be EOS token. Okay, so here if you see, we would have provided the same pad token is equal to EOS token. Now we are setting the ID to be EOS token ID. Okay, so that is about the generation config. And now I'm calling the time, and inside that I'm calling the time.time function so that we can keep a note of start time. And once we call the model.generate function star inputs, why star is because it will be in a form of dictionary, and to load the dictionary you need star so that all the keyword arguments will be passed accordingly. And then we are also providing the generation config. So by this we are getting the output token IDs. Okay, and we are decoding it by skipping the special tokens. Once you decode it, we are printing it. Also, we are printing the time and the summary, which is Vasant is at railway station. Everything is going smoothly. He will meet Karthik soon. Is on point and accurate. So yeah, guys, we have seen that Mistral is pretty good, and yeah, like they have said, Mistral is an open source beast. It is the best 7B model right now. So I hope you will all try to make this model with your own use case, and let me know if you have some interesting use case which you have done with the model. I'm very interested to know the potential of this model with the different use cases. I have an interesting use case which I'm working on right now. So soon I'll make an announcement of that as well. Probably in 1 or 2 videos. The next video should be the use case which I'm working on right now with Mistral. It has shown some potential. I'm just tinkering it a bit rather. So yeah, guys, Mistral has shown great performance, and we have seen how to fine tune it for your own use case to harness the potential of this model. So I hope you all like this video. That's it for this video, everyone. Please hit the like button and subscribe to the channel. Hit the notification button so that you will all be getting the notification while we premiere or also upload the video. And more importantly, guys, share it with your friends, because this is a model everyone need to know about. So share it with your friends and community, and comment your opinions in the suggestion. Okay, I'll see you all in the next video, everyone. Until then, cheers.